Here's our objective, all right? And that's what we're trying to figure out. Why don't they behave ideally? Now, is that a Lewis-Dirac diagram of halogen? Yes. Are those what electrons look like on the valence electron? No. Valence shell? No. Is this a Bohr theory atom? Yes. Is that really what an atom looks like? No. Pervnert is similar. The ideal gas law is similar. It's an oversimplification. Why do we do this? Because it helps. It's easy. It helps show a lot of relationships. And oftentimes the real things are a little more complicated. And it's good to have an understanding of an ideal scenario before you go into a more complicated scenario. The reason this exists, reason Pervnert doesn't work, is because particles, they're always are going to take up some volume, whereas the ideal gas law says, hey, they're like these pinpricks, space, and they're always going to have some attractive intermolecular forces. Sometimes it's negligible, sometimes it doesn't. It's really good to know when it's behaving ideally. Gases love high temperature and volume. Lots of energy, lots of space. They like low pressure, small IMFs, or when the particle sizes are small. And non-ideally, it's basically the opposite of those conditions. All right? It could be a mixture of them or one or the other. All right? Now, we're going to go over some scenarios of what makes things behave unideally. There's like this table you're going to set up. I'm going to talk about one variable, what its effect's going to be. I'm going to give you a visual. It's the back. It's the back of the slide of the PowerPoint, and what that effect has on the gas. It's really mainly going to be expressed in temperatures, and I do the visuals last and give them plenty of room so you can draw. All right. My first variable is increasing the intermolecular forces. What happens if I increase the intermolecular forces? Well, the more attractive they get, what happens to the gas when they tend to hit? They're going to stick. And if I have the gases stick and form these like groups, then as they move around, they're going to interact with the walls of the container and each other less. Therefore, my pressure will decrease. Therefore, like I said, my pressure is going to decrease. Here's our visual. Because the particles are sticking together, all right, my actual pressure would be less than ideal, less than what I predict using the IMF. Now, the low temperature is really going to be similar, except what's going to end up happening here is if it's really low temperature, the gas tends to get sluggish because it doesn't have a ton of energy. And then when it collides, when things are, its low temperature allows these IMFs to have a greater influence. Therefore, it's going to end up looking like this. And you're going to see a similar effect in that the gases will tend to stick together because now IMFs are playing a greater role. And once again, my pressure will be less than you'd expect using the ideal gas law. Now, at high temperatures, the gases are like really happy. They don't care. They have enough energy when they hit. They don't bounce. They don't stick because they've got so much energy. So this is what it looks like, and your IMFs are negligible, and you don't have any deviation. Now, for particle size, what happens if the particle size goes up? What happens? Well, as you can see, I basically doubled the size of each particle. It's just going to tend to be more collisions, all right? Because your particles are so much bigger and they're taking up so much more space that your pressures would tend to be more than you would expect. They'd be higher than you'd expect them to be based upon the ideal gas law. Now, a low volume is kind of similar. Whereas I take these and if I put them in a low volume, that's a little bit glary, particle size tends to have more and more of an effect because all your space is being used up, and you're going to have more collisions than you'd expect using the ideal gas law, and your actual pressure will be higher than the ideal. Now, low pressure, here's what gases like. They like not a lot of space between it and its neighbor. They want to move around and be free and be a gas and just go wherever they want to go. So your particle size at low pressure is basically negligible. All right? And high pressure, that's what it looks like. All right? High pressure, your particle size tends to have more and more of an impact. And what's going to end up happening is your actual pressure might be higher. Now, you'd actually be changing the volume or the temperature to incur this temperature degree in high pressure. You can't change pressure. You'd actually be changing the actual and ideal. Sorry, no, the volume or the temperature to affect pressure. All right? Good. I hope that was helpful. Have a good night.